So hey everyone, let me share my screen. So welcome to Multimodal Weekly. This is a weekly webinar series hosted by 12 Labs. For context, we an early stage startup building multimodal foundation models for video understanding. We've been meeting on a weekly basis over the past almost 2 years or so. And here are some topics that we tend to cover on a weekly basis. New research in multimodal AI and foundation models, the innovative application of multimodals in different verticals, different video and interesting multimodal projects from our community members, and finally talks from our internal teams about how to use our technology platform and API, etc. So we've been doubling down a lot on research, over the past several months. With the webinar, we have talks from researchers working on a variety of interesting topics, ranging from generic, reasoning for video understanding, agent for tool use, different video editing approach, retrieval problem, multilingual, multimodals, generation, etc. And so for today's session, we'll have all the speakers actually focus on a specific domain of research. So we're super excited to have this list of presenters today to listen to their thoughts and hear about some of the latest perspective from their field. So to get started, we'll have Sherry Sre, currently a PhD student at University of Texas Austin. She will present a project called HOI-Swap, which is a novel diffusion-based video editing framework trained in a self-supervised manner. And secondly, we'll have Jyun-Ting Song, currently a master's student in the robotics lab at Carnegie Mellon University. He will present his work called Harmony 4D, which is a multi-view video dataset for human-human interaction, featuring in the wild activities like wrestling, dancing, MMA, and more. Third, we'll have the joy presentation from Yicheng from Institute of Sun in Tokyo, and Yuxin Chen, currently a PhD student at UC Berkeley. They will present their work called Regression-based Analytic Incremental Learning, which use an approach to learn from a sequence of domain in a non-forgetting manner and decouple the cross-domains correlation by projecting features to high dimensional space. And finally, we'll close out our webinar session with Dr. Yue Tan, who's based out of University of New South Wales in Australia. She will present the work called ViLCo-Bench, which is the first dedicated benchmark designed to evaluate continual learning models across a range of video to text tasks. Yeah, so I can see there's a lot of exciting work that we cover today. For the audience, feel free to send your question on the Zoom chat, and I will collect them and share them with the speakers, as they go through it. And then, I think after each session, we're going to have a short Q&A interactive chat, for them, so we can ask any real-time question. So with that, I will stop sharing my screen, and I will enable screen sharing for Sherry. I will also let you unmute. And now, yeah, go ahead.
Can you see my screen?
Yeah, I can see the second slide of your screen. You can guess from the beginning. That'd be great. Awesome. Yeah.
Hi, everyone. Thanks, James, for the intro. So I'm Sherry. I'm happy to be here today presenting our work, HOI-Swap, swapping objects in videos with hand-object interaction awareness. So let's first discuss the problem scenario. Consider a video depicting a hand picking up a kettle like this. Imagine watching this video, and what if right now we want to swap the kettle here with a different object specified by the user? It could be a different kettle or a differently shaped bottle or bowl. And this is a problem we tackle in our work, how to seamlessly swap this in-context object in videos. This capability can transform video content creation in entertainment and also has great potentials in robotics. Imagine you have originally only have a single video, but with this feature, you can create multiple versions of the same video, but manipulating different objects. However, Existing handling hands in video editing is notoriously difficult. Existing generative models struggle with this task due to three challenges. First, there's this need of hand-object interaction awareness. Let's see. If we want to replace a cattle with a ball here, it necessitates some pattern changes in terms of how the hand should interact with the object. And we see that the current implanting approaches, although they do well at general like object swapping tasks, but they still fail to create realistic interactions involving hands. Second, there's this issue of spatial alignment. So let's see the example here. We have the new object is a cattle, but its handle is on the left. And in the source image, the cattle's handle is on the right. So the challenge is we want to like reorient the new object to make it align with the scene context in the source image. However, we see that existing hand insertion approaches, they do not offer such level of control. So they can, well, this is like our desired outcome. Finally, there is this challenge of motion transfer. So existing video editing approaches enforce strict motion alignment. They are using conditional signals like to transfer the motion from the source video to the target video. The majority of them adopt shape-related motion signals like step sequences or optical flow sequences. However, this is not very flexible. Say we want to replace a ball with a cattle here, there are some shape changes. And if we directly adopt them, they actually fail to adapt the motion accurately, as can be seen from the generated results of existing models. And this is the outcome we aim for. So to address these challenges, we introduce HOI-Swap. It is a video editing framework that incorporates hand-object interaction awareness, ensures accurate spatial alignment, and provides controllable temporal alignment with the source video's motion. Here's a preview of the high-quality results HOI-Swap generate. For training, we consider a self-supervised framework where no paired data is needed, since it's really infeasible to collect source and target video for this purpose. So we formulate it as a video implanting problem. The idea is from the original video, we mask the source object and prepare an image of the same object, but it could be originate from a different random time point in the video. And then the HOI swap is tasked with getting this reference object image and this mask sequence as input and tries to reconstruct the original video. So in this way, the training is purely self-supervised. Now, during inference time, we just replace the reference object with another user-specified different reference object. Since the model learns how to place this object, seamlessly place this object into the masked sequence during training. In the inference time, we get this edited video. So now let's talk about the design of HOI-Swap. We have discussed the overall training framework, and in terms of the editing process, because it's very hard for the model to do the editing in one stage. So to decompose the complexity, we propose a two-stage strategy. And in the first stage, the model is tasked to swap in the reference object in one single frame. So we select one frame, and in stage one, we try to swap the reference object into this frame. Then, in the second stage, it tries to propagate this one frame edit across the entire video sequence, focusing on getting temporal alignment and carrying forward the spatial alignment established in the first stage. For this purpose, we extract motion points from the original video and warp it to the new object. So for the stage 2 model, it takes in this swapped sequence as input to generate the final swapped video. And this is a high-level overview of our HOI-Swap framework. We just discussed inference. So let's break it down and see how each stage is done. In the first stage, we say that it focuses on having successfully do the object swapping in one frame. So it's like an image editing task. Given a hand-object interaction image, we mask the object. And there's this reference object construction process where we try to extract the reference object because we want we don't want this task to be too easy. So we did some augmentation. We take a different frame depicting this same object and do some spatial augmentation to get a different post object. And we collage this object image along with this masked image. With this image, it gets concatenated with noise and gets fed into the diffusion network. The idea is we want the diffusion model to take in this collaged image and learn to reconstruct the original image. And in this process, it learns how to reposition the object back to a realistic hand-object interaction pose. And also there's this branch where besides this collaged image as a conditional signal, we also input this object image. It's encoded by a dyno and embedded through cross attention as condition to the denoising unit. Now for the second stage, the goal is to achieve controllable motion-guided video generation. So now that we already have one frame edited, so for the second stage, the training is we first select one frame as a conditioning frame, and then we try to carry out the motion information from the source video. Specifically, we extract the optical flow, use the selected frame as an anchor frame, and then sample a few points within the masked region, so that with this information, we can have a warped sequence that look like this. And this time, we train a video diffusion network which takes this warped sequence as conditional signals, and we task it to generate to reconstruct the original video sequence with a standard L2 loss. Also, the conditioning frame here is encoded by clip and embedded by cross attention as condition to the denoising unit. So now let's look at some quantitative results. We see that HOI-Swap consistently produces high-quality edits with realistic hand-object interactions. It significantly outperforms existing methods in both quantitative and qualitative evaluations, including a user study. And let's take a look at some qualitative video results from HOI-Swap. So the left one is a source video, and this is a target object we want to replace, and this is a generated video. This is a source video, and this is our HOI-Swap generated video. Notice on these examples how our HOI-Swap learns to adjust the grasp patterns to suit the swapped object. And for this example, how our model learns to reorient this object to align naturally with the hand and scene context. And here's a comparison of HOI-Swap with state-of-the-art editing approaches. You'll see that these existing methods, they often produce unrealistic edits because it's really a challenging problem to address these hand-object interaction regions. And our HOI-Swap maintains high-quality, coherent edits. Here are just more qualitative results. Here we are showing results on dataset, like showing its zero-shot generalization capabilities on datasets for which HOI-Swap has not been trained on. And finally, there's this ablation study where we investigate the warping process. So we can actually, by controlling the number of motion points we decide to sample, we can actually HOI-Swap demonstrates this controllable motion guidance. So this is the original video, and if we do not sample any points here, it will generate the video like that. And if we sample more points, it will, this is how the generated video looks like. And if we sample 100% points, this is how so we see that they are kind of different, and it shows that by varying this sampling sparsity, we can get a spectrum of videos that more or less follow the motion guidance from the source video. And thank you for listening. I'm happy to take any questions.
Awesome. Yeah, thanks a lot, Sherry. So perfect. If you have any question, feel free to either put on the chat or, unmute yourself. Maybe one question from my end to get started is, what are some of the application use cases that you think for this work?
Yeah, so it's like, as I briefly discussed in the beginning, we could imagine it be quite, like say just for entertainment in your daily life, you already record a video, and it has maybe it has an object. Now you are thinking if you could just get a same version of this video, but with a potentially different object. Like it saves manual editing. It just saves effort on manual video editing. And for robotics, like it has potentials as a data scaling approach because you only need to collect one video data, and then you could seamlessly just run the model and get multiple versions of the same hand object interaction pattern, but with different objects as some data augmentation.
Perfect. Looks like there's a question on the chat from Sunil. How difficult it is to have the swap when there are two identical or similar objects in the frame?
Yeah. So thank you for the question. So the idea is we would so it's like during inference time, we could specify which object to replace. So it's specified as a bounding box. So if we want to replace object one, then we will put a bounding box there and ask the model to replace that one. So it's one at a time.
Great. I also take a look briefly at some of your previous research and existing research. Looks like you're also working on video frame captioning, right? As one of the current projects.
Yeah.
Would you mind sharing a bit some details on that one?
I think so the idea is within current we propose problem we propose something called video frame captioning. Well, the idea is for image captioning, if we just say for a video sequence, if we just individually caption every frame, then the frame captions are isolated. They do not have the temporal global context. But if we just take the video and use a video captioning model, then it's more like giving us a video event level overview of what is this action, maybe say scrambling X, but what's the progression of this action? say, let's say whipping cream, like which, like for each individual frame, like say for this frame, what's the stage of whipping cream? Is it done yet? Is it 70% ready or 50% ready? This kind of like more fine-grained progress or well captions are actually lacking, and that's what our that work is trying to address.
Great, awesome. Yeah, looking forward to see it. I think due to the time, I think we should probably like push it to the second speaker. There's another question in the chat, so Sherry, if you want to answer it,
I can answer it in the chat.
Yeah, asynchronously, that'd be great. So I think next speaker is going to be Jyun-Ting. So yeah, feel free to go ahead and then talk about Harmony 4D.
Okay, thank you. Let me share my screen. Thanks for the invitation. Hi everyone, my name is Jyun-Ting Song. I am a second-year master's student at Robotics Institute, Carnegie Mellon University. And today I'm going to present our work. It's Harmony 4D, which is a multi-human data set for close human interactions. So I know that not everybody is from this field, so I want to have a quick recap about what is human pose estimation. This is actually a very classic problem that given an image, you ask your model to tell you what is the location of your shoulder, or the location of your elbow, your wrist, your knee, or your ankle. And this applies to both 2D and 3D. So there are 2D pose estimation and also 3D human pose estimation. And just like all the other computer vision text, we want to train a deep learning model to do this. But to have a to train this kind of model, we need a suitable data set for it. However, let's think about how do we have this annotation. So for 2D pose annotation is quite easy. You can just ask people, give them this image, ask them where's the location of each joint, and they will tell you, they will draw this on the image, and this is easy. But how can they draw this in 3D? It's very hard to do this to get 3D pose annotation. So traditionally, what they do is that they will have this motion capture system, is that you have an individual wearing this tight suit attached with multiple markers on you. And there are a lot of expensive cameras in this mocap room, and this camera is track these markers. Then you use these markers to calculate your 3D joints location. And obviously, this approach has some problem. Is that first, you can only do this in a lab environment, right? Its like scene diversity is always the same. It's always the same location. And second is this equipment is very expensive. I actually don't know how much is it, but I cannot purchase it. And the most important problem is that it's possible for the model to cheat, because when your individual is wearing this, you have a lot of markers on you, then your model might not learn where is your shoulder. It might learn where is the marker, and then you use the marker to infer where is your shoulder. So it's cheating. So we don't want this happen, and it also makes it harder to generalize to in the wild images. So to bridge this gap, we also this is another existing 3D human data set, like human 3.6M, 3D PWL, very famous, but not all. So they all have some limitations. For example, like human 3.6 is single human. This one, it lacks human to human interaction. And most of them are captured in lab environments using motion capture system, I just said. So to bridge this gap, we present this new data set. It's called Harmony 4D. It's multi-human. It has a lot of human-to-human interaction, and it's close human-to-human interaction, and you can record this at anywhere. So this fixes the scene diversity, and you don't need a motion capture system to get the 3D joints location. All right, so how do we build this markerless multi-view capture system? We don't want to use those expensive cameras, so we only use GoPros and also ARIA glasses from Meta. And our setup is that all the individuals will wear the ARIA glasses, and we will have a lot of GoPros. We have 20 GoPros surrounds the whole scene. Then to give you a very easy how does a markerless capture system work is that first from all the GoPros, you first get a bounding boxes for each person. Then you get the 2D poses using for example, you can run 2D pose estimator. You can get a 2D poses for each human. Then you do triangulation. Then you can get a 3D poses for each individual in the scene. And this approach actually works, and it actually works pretty well. For example, in EgoHumans, their 3D key points are very stable, accurate, and easy to process. But there's some problem of EgoHumans. Is that when two people are in close interaction, for example, when two people hug each other, then it would actually generate incorrect 3D poses. And you see that in this image, the legs are not on the same person. So why does this happen? So the challenges is here is that when two people are in close interaction, first, some of the key points are invisible. Also, some of the key points are ambiguous. You don't know which parts of the body parts belongs to which person. Yeah. So in this case, if you get a 2D poses from a bounding box, it's very unreliable. Then when we do a triangulation, it will fail. So how do we get this? How do we get this reconstructed human? Our intuition is that we want to utilize segmentation mask, and we want to use person-specific segmentation mask. And why do we want to use it? Is because a segmentation mask provides the information to differentiate body parts for individuals. So this helps us fix the ambiguity issues for the key points. And if you have a good segmentation mask, it's possible to infer the occluded key points from it. So for example, on the image on the right, if you have the blue mask, then you can kind of infer the shoulder joints of this person based on this mask and the image. And that's our intuition. So how do we get a good segmentation mask? What we do is that first we have this multi-view images for the same timestamp. Then we do triangulation, get these 3D poses, and we pass that to our human motion model. And this human motion model is a tracking model. Then it will generate a 3D poses in the next timestamp. And using this 3D poses, we will project this predicted 3D poses to 2D. So now all the cameras has these 2D proposed key points. Then we pass that to segment anything. Then we can get this kind of segmentation mask. Now we train another new 2D pose estimator. This 2D pose estimator, it takes the RGB image and the segmentation mask as input. Then it outputs the 2D key points for each person. And why does this pose estimator better than others? Is because it has the segmentation mask information. So you can see like from person A, this image, these two, if you have the max, then you don't worry about the ambiguity of the key points. And the right leg, although it doesn't have the segmentation max, our model can actually infer it from that. So now we have a reliable 2D process. Then we can do a triangulation. So I want to recap this PyPy is that we have this multi-view image. We first have this human motion model to predict the 3D poses in the next timestamp based on previous frames. Then we use this predicted 3D poses to get the segmentation mask. Then we use this, we have a new 2D pose estimator. It takes the RGB image and the segmentation max, and it outputs reliable 2D key points. Then we do triangulation. Now, this triangulated 3D poses is reliable, and we use that to predict the motion in the next timestamp, so that we can. So next, we will predict the timestamp in the next one again. We get the 2D key points. We get the segmentation max again. We get the 2D poses from the segmentation max again. Then we do triangulation. We keep doing this, and it forms a loop. Then for the whole sequence, we can get all the 3D poses correct. And apart from the 3D poses, we also feed the SMPL human meshes, which is a human parametric model, to our dataset. This also benefits other like human mesh recovery, human reconstruction area. We hope this will be beneficial. And we also do some experiments. The left one is image, the left second is ground truth. The other three are a Stota method. We found that the existing methods struggle on our data set. And when we fine tune it on our data set, they can actually have a better depth estimation, joint ambiguity differentiation. So this proves that our data set is variable. Okay, so this is our dataset, Harmony 40. It has 1.7 million images, a large-scale multi-human dataset. And we have released the code and data, and we hope this dataset can be helpful for this area. Yeah. Okay, and that's all from my side. Thank you so much.
Awesome. Yeah, thanks, Jyun-Ting. Really appreciate your walking through this work. Yeah, so any question from the audience, feel free to put it on the chat. Maybe one question from my end is the yeah, what could be some of the limitation of this data set in your opinion?
Okay, so there are a lot of limitations actually. So right now we don't have the finger key points, and finger key points is because of the resolution, we cannot get accurate finger key points. Also, right now the mesh reconstruction is not perfect, so you can still see some error from the mesh reconstruction, but this is not our original target. Our target is to get joint locations, right? And the 3D reconstruction, this involves the shape. We need to estimate accurate shape from it, but our pipeline doesn't have this for now. Yeah, these are the two limitations I have for this data set.
And I know that you're working on the robotics lab, right? At CMU. So you're working on the robotics lab at CMU, right? So it sounds like this application can be pretty relevant for robotics research.
Yes, it is. I think mostly this application will be AR and VR. Yeah, and I previously worked on robotics, but right now not so much actually. Yeah, I'm making that transition. Yeah.
Noted. Awesome. Yeah, so if there's any question for Jyun-Ting, feel free to put it on the chat. You know, I want to pass it on the third group of presentation so we can go over the remaining talks. Yeah, so Yuxin and Yicheng, feel free to just unmute and share your screen.
Okay. Can you see my share screen?
Yes, I'm seeing it. Very nice.
Okay.
Thumbnail.
Okay, so let me get started. Hi everyone, I am Yicheng from the Institute of Science Tokyo, and my friend Chen is from the UC Berkeley. Thanks for the invitation to the webinar, and I'm going to introduce our paper of advancing cross-domain discriminability in continual learning of vision language models. So in the era of large models, a foundation model is pre-trained on a large-scale dataset to thoroughly learn general semantic information, where the training data are pre-collected static datasets. However, such large models still show limitations in specific domains, and it may fail to incorporate the most up-to-date data. Therefore, to incorporate the general knowledge of pre-trained models with newly incoming data, we need to continually transfer these models to streaming datasets from diverse domains, which is known as continual learning of pre-trained models. For example, the large language models are required to continually learn the latest news. So the most representative continual learning setting, named as class incremental learning, it aims to enable models to continually learn from sequentially incoming data of different classes, allowing the model to recognize an ever-increasing number of classes. However, this may limit the capability of a large pre-trained model in the early stage of continual learning, as it can initially only classify a very limited number of classes. Such limitation naturally does not exist in the open vocabulary-based models. By incorporating the zero-shot ability of pre-trained vision language models, a recognition system can not only classify newly learned classes, but also recognizes unseen classes. Therefore, the multitask incremental learning setting was proposed to let the VLM continually learn from multiple domains, evaluating continual learning methods by monitoring the performance on both seen and unseen domains simultaneously. However, such setting assumes that the model knows the domain identity of the test image during inference, which does not align with practical scenarios. To address this, we propose a novel setting called cross-domain task-agnostic incremental learning, XTIL. In this setting, the model is required to continually learn from data streams across various domains while maintaining cross-domain discriminability. This means that during the testing, the model does not know the domain of the test image, and the model must identify its specific class from a broader class set. So the challenge here exists in the proposed XTL setting are listed here. First, the vision language model zero-shot ability is required to be preserved when the model is training on additional data. Second, the model shall be able to distinguish data across different domains. Third, the continual learning methods should alleviate catastrophic forgetting on newly learned domains as much as possible. We address these challenges individually by the following solutions. First, we simply freeze the pre-trained vision language model to keep the zero-shot ability on unseen domains. We use the regression-based methods for classification and cooperate them with nonlinear projections to make the features from different domains more distinguishable. Third, we extend the closed-form solutions of the regression to a continual learning manner for the absolute memorization. To verify the effectiveness of the nonlinear regression we tend to use, we conduct a very simple classification experiment on 10 datasets. As shown in the figure, both primal and dual regression methods can classify images into their respective domains accurately without any domain identity hint. These results suggest that a proper nonlinear projection can enrich vision language models' extracted features, even though the projection layer is not trainable under any supervised learning methods. Next, since the model is required to incrementally transfer to different datasets, which means that the model cannot see all the target datasets simultaneously, we extend the standard solutions of both regression methods and to the continual learning forms to fit our setting. While the optimization target here is to map the nonlinear projected features to one-hot labels, the corresponding closed-form solutions are shown here. So we derive both solutions to continual learning forms, where the parameter at each learning phase is solved based on parameter at previous phase and the memory matrix M. You can see here the parameter at nth learning phase is solved based on the parameter from previous step and the current data set and the memory. So each solution is equivalent to its corresponding standard solution of joint learning on all encountered data, which means that it achieves absolute non-forgetting on all learned knowledge. So similarly, by expanding the kernel matrix along the diagonal, the parameter alpha of the dual regression can also be obtained recursively, and it is also equivalent to its standard solution. So here we present an overview of our proposed methods real. During the inference, the vision language model first determines if the test image belongs to seen domains or unseen domains through the zero shot. So if the predicted classes does not belong to the seen class set, the image is regarded as an out of distribution sample, and the zero shot prediction is taken as the final prediction. If the predicted class belongs to the seen class set, the image is regarded as an in-distribution sample, and the OD class scores within the zero shot prediction are masked. And the prediction is then refined through the real adapter. The final prediction is a weighted sum of the real adapter prediction and the zero shot prediction to avoid overfitting. For the training stage, on each continual learning stage, the pre-trained clip is kept frozen and the real adapter is trained on streaming datasets. The orange block here is the predefined nonlinear projections, which is explicitly defined in the primal real and implicitly included within the kernel method in the dual real. The parameters W and alpha are solved based on the aforementioned recursive solutions. So to evaluate different continual learning methods under our setting, we continue to use the evaluation metric in previous benchmark, which is specifically designed for a continual learning of the vision language models. Each block here records the model's performance on each domain at each learning phase. Here, the blue block records zero shot performance. We average across all the learning step of each domain to indicate the extent to which the zero shot ability as the transfer score. The green blocks are the performance at last learning step. We average across all the domains to indicate the learner's adaptability to new domains as the last score. Additionally, each orange block is the average accuracy of all learning steps of each domain, and the average of all the orange blocks serves as an overall evaluation of the performance. So the comparison result is shown in the table. Our proposed methods of both primal and dual forms real methods surpass existing SOTA methods on all metrics. So we further present the accuracy curves of some domains over the continual learning process. We can observe that the zero shot performance remains unchanged before learning the corresponding domain, indicating that the learning unrelated dataset does not affect model's zero shot ability over this domain. After learning it, the performance also does not decline as the model further learns additional domains, suggesting the non-forgetting ability of our proposed methods. The speed analysis shows that our methods are significantly faster in training than the previous SOTA methods. This is because our method does not require any reference dataset. It trains only one single layer, and it requires only one epoch. So to summarize, in our work, we propose a novel continual learning method, REAL, to incrementally adapt pre-trained vision language models to multiple domains without forgetting prior or newly learned knowledge. We propose a new continual learning setting, XTIL, to evaluate vision language models' zero-shot preservation and adaptability to new domains. We show that REAL can memorize incrementally learned domains and preserve vision language models' zero-shot ability while achieving total performance on both MTIL and XTIL settings. In the next step, we will try to extend Rails framework to a broader application case, such as continually enhancing multimodal large language models understanding capability of diverse tasks, not only limited to classification. So you may refer to our paper and the report using the QR code here, and thanks for watching. Next, let my friend Yuxin to facilitate the QA session. Please feel free to ask any question.
Great. I guess one question just right away from is like, what are the upcoming tasks that you what are the upcoming tasks in domain that you want to explore?
You mean upcoming tasks?
Yeah. So I think in the last slide, Yicheng, you just mentioned you want to expand beyond the 10 domain, right?
Yes. So the major limitation of the current work is that we focus mainly on the image classification tasks. But the more interesting task will be the video classifications, or in terms of robot learning, how to continue to learn new motor skills from demonstrations. Because usually, like for the everyday robotic tasks, we have some pre-trained model to do the tabletop task, for example, pick up a cup or something else. But like, what if we put this robot to new environments, and we want to keep the robot's original obtained skills while obtaining some new skills, such as wash a dish or something else. We plan to apply the same logic, but into the motor skill learning of the robots.
And like, in order to apply this same approach to video, what are some of the like challenges in terms of like compute and complexity of like the video modalities that you think you will encounter?
Yeah, so currently we use image classifications, so all the labels are pretty well defined. But like for different pictures, a picture of cat, a picture of dog, it's kind of easy to define those labels. But for the video demonstration, for example, the robotic task, it's pretty hard to actually segment into different semantic video clips, basically, because for a one long horizon task, you have to split into different motion primitive. For example, if you just try to pick up a cup, you have to lift the arm, approach the cup, and then close the gripper. So those additional requirements need more labors, basically, to actually fine-grain labels those demonstrations, and that is what we're currently exploring. Hopefully we can extend this to the high dimension, because the motion is much higher dimension than the image classification tasks.
I see. And I think you personally working on robotics research, right, at Berkeley?
Yes.
Yeah. And any exciting direction?
So currently we're focusing more on humanoid or embodied AI. There's a lot of new humanoids coming in Berkeley right now. So we just try to do the whole body manipulations, and also the robot learning is always a hot topics. So how to continually learn those skills through the internet skill human demonstrations, the robot demonstration will be a very challenging but exciting directions in the future, I would say.
Yeah. I forgot to ask, but what is the base vision language in? Oh, you use clip, right, for this work?
Yes.
Yeah. So just like a pre-trained clip for image and text encoder.
Yes.
Okay, makes sense. Yeah, I think that's all the question I have.
Yeah. Thank you.
Yeah, so if there's any more question for Yicheng and Yuxin, please put it on the chat, and I think they can answer them. So we got about 15 minutes left, so I'll let the last speaker, Yue-Tan. She's actually going to talk about continual learning, so I think it's a good follow-up to your talk. All right, sweet.
Okay. Can you see my screen now?
Yep.
Okay. Hello everyone. Today I'm presenting our recent work, which is titled ViLCo-Bench, Video Language Continual Learning Benchmark Accepted at NeurIPS 2024 Dataset and Benchmark Track. My name is Yue-Tan from University of New South Wales. I'm presenting it on behalf of all the authors, led by the team of Flora Salim. So in this work, we propose a novel benchmark for video language continual learning frameworks. Here we give an example of our video language understanding task. The question is a moment query based one. For example, given the video above, the question is, when did I put the wood log? And the expected output answer is the temporal window corresponding to this query. And one crucial challenge in this multimodal learning scenario is the continuous adaptation. There are usually new data, new tasks, and even new query types. In this multimodal scenarios, each mode of data can evolve together or separately through the emergence of a new task and also the emergence of new data distribution. And a model that can adapt to all these kinds of changes is needed. But before that, we need an evaluation benchmark too. That's the motivation of our benchmark work. And current continual learning benchmarks are typically designed for the static unimodal data, such as images or text alone. However, real-world applications like robotic and autonomous systems require models to adapt to continuously incoming data from multiple modalities. Our goal with ViLCo-Bench is to create a benchmark for this, and we prefer to see that a benchmark that allows continued learning from both the video and text data in real time. And ViLCo-Bench offers the first standardized benchmark specifically designed for video language continual learning. And in comparison with other continual learning benchmarks, ViLCo is more challenging by providing long-term videos and flexible language descriptions, and also providing a larger number of tasks and samples. This figure shows an overview of ViLCo benchmark pipeline. First, we create a set of video language data with corresponding annotations. And then we propose and build 3 unique video language continual learning tasks to evaluate existing continual learning methods. And our main contributions include the creation of 3 distinct video language tasks, which are moment query, natural language query, and visual query. All of them go beyond traditional classification tasks. And the third part of the baseline, the pipeline is that we propose a memory-efficient framework using the self-supervised learning technique and an episodic memory module to better manage the complexity of continual multimodal learning. And finally, we provide the empirical study to get the evaluation results on ViLCo and produce a leaderboard of ViLCo. For the data curation part, we sample video language data from the Ego40 dataset, which is an egocentric multimodal dataset. The first type of task is moment query. It focuses on identifying the moments in video regarding an activity in the video. For example, here the question type can be, when did I fold clothes? And the expected output are all temporal windows related to this activity. This task includes 110 different activities in total. And the second task is the natural language queries tasks. It involves open-ended questions such as what color was the tent? And the output is also the temporal window where the answer is visible. It includes 13 question templates in total. And finally, the question tab is the visual query task. It requires locating the objects in the video, such as where did I see this brush? And the output is a 2D bounding box, and there are 2,000 clauses in total. These tasks reflect the real-world complexities that existing benchmarks cannot well address. We also introduced a multimodal continual learning method based on the framework shown here. Specifically, our framework includes 5 parts, which are the encoders for different modalities. Here, it includes the wish encoder part and the text encoder part. And the second part is the cross-modality encoder part. It aims to further fuse the output, the embeddings of different modalities. And the third part is the memory module, which includes both the short-term memory buffer and the long-term memory buffer. And the last part is the task-specific headers, which are designed for different specific tasks. There are 2 main technical contributions here. The first one is the episodic memory module, which maintains both the short and long-term memory, helping the model to retain context across tasks. And the second contribution is focusing on the self-supervised learning module. It is designed to mitigate the challenge of limited label data. It mainly uses the video narrations to align the video and language representations. Together, these components allow the model to handle complex and continuous inputs more effectively. For the experimental part, we carry out separate experiments for each type of task and obtain the performance of ViLCo and existing continual learning baseline methods. Here, we conduct the separate experiments for each type of tasks, and then we investigate the impact of different visual encoders as well as different visual features considered in the whole framework. And the last one is we have verified the effectiveness of our designed episodic memory module and the self-supervised learning module. This slide shows the results of the state-of-the-art methods and our methods on moment query and natural language query tasks. The evaluation metrics used here include the average recall rate. Specifically, we use the IOU as the reported evaluation metrics and the backward forgetting score to evaluate the memory stability across the continual learning procedure. We also report the upper bound and the lower bound of the proposed benchmark for each task. These bounds represent the multi-task learning setting where all samples are available or not to the model throughout the whole training process. It can be observed that the performance varies dramatically across tasks, but our methods using the episodic memory module and self-supervised learning mechanism performs better than both the replay-based continual learning methods and the regularization-based ones. As for the ablation study, we investigate the impact of different visual encoders and visual feature extraction strategies. These, for example, for the table 5, it mainly the implementation empirical study on the impact of various visual features. We utilize different visual visual encoders as a backbone and verify the robustness of our methods and the whole benchmark on different backbone settings. And the table 6 below shows the impact of various visual features. We integrate different techniques to pre-process the visual features here, and also to evaluate the robustness of the methods. As for the table 7 here, we do the ablation study by removing either the episodic memory module or the self-supervised learning module, or both of them, to evaluate how these modules contribute to the final performance improvement on the benchmark setting. For more details on our benchmark and detailed discussion, it is welcome to refer to our paper. And thank you for your attention. We invite you to explore the benchmark further by visiting the GitHub page or the original paper. Yeah, you can also find the full dataset and source code on the GitHub page. And thank you. Any questions?
Great. Thanks, Ray. Looks like there's a lot of experiment that your team has run, and very, like extensive experiment, compare different impact. So yeah, this seems to be a very comprehensive benchmark. So one question I have is Ego 40, right? That is the base data set. And
Yes. Yes, it's an egocentric data set published in recent years. Yeah.
So you curate from that massive data set into like a subset, right? That fall along these three categories, right? Movements, natural language, and visual.
Yes. These kind of tasks have already been included in the Ego 40 dataset since its release. We just do the fine-grained formulation of different tasks. For example, we formulate different subtasks under different main task categories to better formulate the whole continual learning process.
I see. And I think in your in your table about the impact of different base model, right? There was a table that you mentioned, transformer and intern video. Yeah. So
Yeah.
table 5. So which one is like the best visual backbone in this scenario?
As the results shown here, the as for various visual backbones, we found that the Ego VLP version 2, this backbone performs the best over the benchmark setting. Yeah, and that's also what we utilized in other experiments.
Oh, I see. So because you run table 5 first, right? You choose the best visual backbone, and then you run table 6. You use Ego VLP.
These are further video processing techniques included here. And we can see that after incorporating the intern video, I think it is more useful to incorporate with the Ego VLP visual benchmark, because it further improve the recall rate for different evaluation metrics.
In your diagram framework, can you go back to the framework diagram? Yeah, there's a lot of steps, right?
Yes,
in this architecture. Can you explain the part between selective forgetting, long-term buffer, and memory retrieval again?
Okay. So here we include the episodic memory strategy here. There is one short-term buffer, and the downside here there is a long-term buffer. This memory buffers mainly aims to store the embeddings from different tasks and different modalities here. And when doing the following tasks along the continuous learning sequence, the previous features will be extracted from the both these two buffers and to help compute the contrastive loss to help the current for example, for a current task, we will extract the most similar and most useful representations from the short-term buffer first, and to regularize the model training process. And for the long-term buffer, there will be a selective forgetting strategy to partially forget the long-term memory, and to help the whole episodic memory buffer to work more efficiently. Yeah.
I see. Yeah, so you pretty much like separate short-term and long-term into like two bucket, and then you try to strategically use forgetting so that it can the approach can tap into the right buffer right at the right moment.
Yeah, it aim to make the memory module to be more condensed and to be more memory efficient.
Great. All right. I think that's all. That's the question I have.
Thank you.
Yeah, and so it's a time. So yeah, thanks again, Yue, for sharing your talk today. Thanks again to the speaker as well. Yeah, I think there's a lot of interesting information that's being shared throughout all the presentation. And there's some similarity as well, right? Like across continual learning, across dataset benchmarking, etc. So yeah, I hope both the presenters and the audience found this session to be informative. The recording of this session will be available on YouTube probably within the next couple of days. So I'll be sure to share that with you guys so you can have that accessibility and share that with your collaborators. And yeah, we run this webinar on a weekly basis. So we have more speakers coming up in the next few weeks. And you found this webinar to be useful and informative. Good luck to have you join us again for the subsequent weeks. Thanks, everyone. Appreciate your time and hope you have a good rest of your weekend. All right. Thanks, guys. Enjoy.
Thank you.
Yuxin, Yicheng. Bye, guys. Appreciate it.